So good afternoon, everybody. Welcome you back after the lunch. This session will be on architectural planning for rural and urban housing. In this lecture, I will discuss about the structures, RCC structures as well as masonry structures with the load bearing as well as stone masonry structures. So as you have seen in the video film also, there are some of the glimpses of video films that some of the photographs I took from that films to to explain you that how the building used to behave during the earthquakes. So what are the guidelines for the earthquake resistant design for the building? There are different guidelines provided by the Indian standard codes as and first of all with here it is written that the different type of construction practices in India. We are having traditional kacha house. Traditional kacha house, then unreinforced brick, burnt brick masonry house, stone masonry house, and cement concrete block masonry house. Another construction is reinforced cement concrete construction and precast concrete construction. So in this, I have done my research work in case of precast concrete block construction. Precast concrete block type construction. I'll explain you that we have made some interlinking block masonry system with the low cost viscoelastic links element. So in this case, unreinforced burnt brick masonry kind of a construction, we are having two type of construction. One is load bearing type of construction. Load bearing type of construction in which load is taken by the walls only, and in case of framed structure, the load is taken by the beam and columns. Those who are not civil engineers, there are two type of construction. One, we are making beams and columns, and another which we are making our own house for. We are keeping the walls, and after on the walls we are having our roof. So that is called as load bearing type of a construction. Load bearing type construction, we recommend 3 to 4 story building, but in case of framed structure, you can go up to any height by proper design and proper planning. So here first principle for the earthquake resistant design is reduce mass. As we all know that I always relate this our civil engineering construction with our own body. If you'll see that if somebody is having huge mass, or if somebody is having obesity problem, then the balance of that particular person is not good. As in case of our structure also, the mass is a great problem. During any earthquake used to induce inertia force to the building, and this inertia force is proportional to the mass. If the mass of the building is more, then the inertia force will be induced by the earthquake will be high in case of that building. Another is symmetry and continuity. If you are having symmetry in your building or symmetry in your building, then that building will behave very well during earthquake. I'll explain in the in upcoming slides that how the symmetry and the continuity of the structures in that earthquake forces behaves in those kind of structures. Another is ductility. Ductility means we are allowing the structure to move with the forces, a little bit movement of the forces. Ductility as well as damping. What is the damping? Damping means whenever one force used to come, so another body resist those forces because of friction, because of some damage. That because of that friction and damage, the energy is absorbed by the system. So that is called as damping of a particular system. In case of masonry building, if some earthquake is there, so first of all, in masonry kind of a building, you are having one brick. After that, you are having mortar joint is there, another brick, another mortar joint. So when earthquake will come, then that the joint, the cracking of the joint, first the cracking of the joint will be there. So because of that, though that cracking, and because of the small movement of the bricks, so that is the damping. That is how the structure used to absorb the energy, earthquake energy. So here, if we are having the earthquake features at the planning stage, that will be better as well as that will be economical. if we want to incorporate the earthquake resistant features, as you have seen in the video films also, the cost of that retrofitting is much higher as compared to if you are having the earthquake resistant measures at the planning stage. So you can save your cost as well as you can have your construction earthquake resistant. See, when we are making our houses, we spend lot of money. Nowadays the construction cost is very high, around 2002, at some places around 2000 rupees per square feet cost is there, and at some places it is around 1200 to 1500 also. So it is a huge cost. If you want to make your small house, you need to spend around 10 to 20 lakhs rupees for constructing your own house. But if that house will in any case of disaster like earthquake, if that house will fall on you, then you are spending that much of money uh, to be killed yourself because of your house. So if you will have small intervention, if you'll have small recommendation of earthquake resistant features, your building will not collapse. It will give you sufficient time to evacuate, to save yourself, and then it will collapse. So these are some of the earthquake features. First, in the first slide, so very important thing is site selection. See, the building used to reside on a foundation. If your foundation is not firm, or if your foundation is not rocky kind of foundation, then your building will not save. Imagine if you are having some filled up land. So first, whenever you used to construct your building, first have this have your have your this foundation need to be checked by the soil engineer, that the what is the soil bearing capacity of your foundation. First you need to check the soil bearing capacity. That is only checked by doing the soil investigations. Then only we can design the building. Then we can decide the foundation of the building, that yes, this house need raft foundation or strip foundation or pile foundation. What is the strip foundation footing? Strip foundation is the wall is having individual footings. That is called as strip kind of a footing. Like this, if wall is there, it is having individual kind of footing like this. So this is called as this is the wall. Wall is having individual kind of a footing, that is called as strip footing. And if our house is having a common this is called raft footing. Raft means you are having a common foundation for all the. Now this is the case where the asymmetric and the continuity comes into the picture. If your building is having T shape, L shape, U shape, and X shape, a particular building is having a particular moment of inertia and particular moment of resistance. So in this T type of building, if you will calculate a moment of inertia, so it will lies inside maybe inside of flange or inside of the web of the building. So the building behave in a different manner. Like this, if you have joined your building, and if you are having no separation joint inside your building, if suppose the force came in this direction, so this wall will behave as in plane wall, and this behave as a out of plane wall. Now what is in plane and out of plane action of the wall? In plane action of the wall, what is in plane action of the wall? Suppose this wall is there. Suppose this wall is there and earthquake force came in this direction. So this direction of the wall, is in plane, because the force is acting in the plane of the wall. And if the force is acting in a perpendicular direction, that for this direction of the earthquake force, this this wall again behave as a out of plane action, because it will overturn. The wall is overturned by the earthquake forces. So at the same time, one wall can become the in plane wall, as well as at the same time that particular wall became the out of plane action of the wall. So earthquake forces at one particular time, earthquake force in can be there in a in suppose northeast north south direction and west east direction. So the earthquake force can come in any direction. So we need to, if that that's why in the we used to say that if you will join your building with each other, then it will behave like a box kind of action. But this L type of structure and this X type of structure, T type of structure, this is very dangerous in case of earthquakes. You can save your structure by providing the small separation joint. These are the separation joint. These are given in the IS code also. This another thing, when you are having the high rise building, suppose 3 to 4 story building, and in that case H by B ratio should be less than 4. You have seen many of the buildings having very small covered area on ground floor, and after that this kind of foundation, this kind of building is there. Why a builder used to make this kind of a structure? Because that restriction of covered area at ground floor is there. So here we are discussing about the H by B ratio of the building. So H by B ratio of the building should be less than 4, and the building should have a larger base than adjoining buildings. The upper stories should have the less covered area as compared to the ground floor. That building is better in case of earthquake forces. So this is how the separation joint look like. If you are having one building like this, like you are having here, one building is there in which separation joint is not there. So when the earthquake force will move will be there, then the ground story will behave in a different manner as compared to the upper story. In case of earthquakes, maybe for the ground story, the earthquake force will be in plane direction, but at the same time the upper story will have the out of plane action of forces. So this is how the earthquake damage will occur in this kind of a particular kind of a building. So if we are having separation joint, then the building will behave in different manner. Here you can see one larger building is there and adjoining small building is there. Another case, if we are having this large and small buildings, we need to design this separation joint, or we need to provide this separation joint according to the codal provision, because we are having ponding effect. Ponding, what is the ponding effect? Ponding effect is that the smaller building, the smaller adjoining building can hit this taller building on a particular on this particular portion, and it can damage your building from here. So it is called as ponding effect. Smaller building is hitting the larger building in case of earthquake, if you are having not sufficient gap of separation joint. So these are the another thing. We are having large balconies, as well as in case of our apartments, sometimes we are not having the sufficient number of columns, and the size of the column as per the Indian Standard Code should not be less than 300 mm, but still we are making our columns 230 mm. That is very very narrow kind of a column. Why we are making this 230 mm of column? Because we used to think that 230 mm of column will flush with our wall, it will not come out of the wall. So because of that aesthetic view, or because of having small space, we are compromising the earthquake forces. So you can well imagine, if you are having very narrow column and it is a very tall height, how it will behave. Because if you are having taller person shake more as compared to the if you are having the wrestler who is having smaller height, and having the wrestler having height of 8 feet like Great Khali. So the wrestler who is having shorter height, it is very difficult to get him down. But in case of a taller person, in case of Great Khali, what is there? If you will just kick him, he will definitely fall because of the height problem, because of this buckling of the column will be there. So these are the separation joint recommended by the Indian standard codes. For load bearing building, the gap is 15 mm. For RCC framed structure, it is 20 mm. For steel frame structure, it is 30 mm. But practically, as we have seen, as we have investigated many buildings, we have investigated one building of NABARD in J&K in Jammu. And there we have seen that the separation joint for the 4 to 5 story building is around 50 mm. So practically possible separation gap is 50 mm. These are the codal provisions. So this is how the liquefaction of the if you are having the soil like black cotton soil, or if the water table is high in your vicinity, then this liquefaction of the soil will be there. So you need to have the raft foundation or pile foundation. In case of sloping roof, in case of rural housing, you must have seen that many of our rural house is having this pitched kind of a roof. Pitched kind of a roof is there. In this pitched kind of a roof, if you want to make this pitched kind of a roof, you need to have the gable bands. Gable bands, what are the gable bands? If you will divide this portion, into two parts, one is triangle and another is rectangle. So in earthquake forces, this triangular part will fall. So that's why we need to provide the gable bands. Instead of this pitched roof, you can have the hipped roof. Hipped roof means you are having the roof band, and above the roof band you are having the roof, so that it behaves very well in case of earthquakes. So another thing, you can have the bracings. If you are having the wooden kind of a roof system, you can have different bracings and on your this pitched roof. So this is another problem. You are having sometime in Bhuj also, one apartment is having swimming pool on its top floor, and this kind of a water tank. This kind of water tank in second picture, I have seen many constructions in Kanpur also, in some of the places in different parts of the country. I have seen many construction that heavy water tank is constructed on the top of our buildings in this manner. So when the earthquake force will come, these columns will fail from here, and this water tank will fall on our building. And because of this water tank, the upper building will be damaged, and because of that additional compressive force and additional moments, the building can be collapsed. So in Bhuj also, two similar kind of a building was there. One building was having swimming pool on its top, and another building, similar building, adjoining to that building, is not having any swimming pool on its top, and that building didn't have even a single crack. But at the same time, the building which is having swimming pool collapsed like anything. So these are some of the features. Now I'll discuss some of the features for masonry construction. So masonry construction, as you have seen in film also, that the bigger wall, larger walls, you should have the buttresses, or you should have the partitions in the wall, because long walls is having unsupported length. Unsupported length means if the earthquake will generate the inertia force to the building, and if unsupported wall, if long wall is there and inertia force will act on that wall will fail in out of plane action, and it will overturn. The earthquake forces will overturn the wall. These are the some of the provision in the stone kind of a masonry building. In case of Latur earthquake building, in Latur, the buildings, small kind of a buildings are made with the arrangement of stones. Stones are placed adjoining to each other. So in case of earthquake, that stone opens up from the middle, and that stone the stone damaged the house, as well as they killed the stone. Because of that stone, many persons were killed. So if to avoid that splitting of the stone, we need to have the through stones. Somebody will ask that if you are not having that much of large stone to be put in the wall, so you can have the small wooden kind of a wooden plank also. You can bend your bar into a S shape, then you can place that bar there, so it will work as a through stone. These are also another problem, that junctions, whenever earthquake is there, corners will open up, and the building is failed from the corners. So these are the two things of the corner. We have provided the through stones at the corner also. These are some of the bands: plinth band, lintel band, roof band. And we need to take care that our opening should be at least away 600 away from the corners, and from each corner it should be 600 away. We should have plinth band, lintel band, and roof band. In case of if your building is residing in zone 5, so these are the vertical bands along with the horizontal bands. These are the vertical bands. Vertical road is provided through and through in the building, in the corners as well as at the corners of the opening, so that it will behave in a single manner. And we used to by this way we need to reduce the unsupported length of our wall. These are the type of the bands which you can provide it. These are the bamboo bands if you are not having the steel in case of rural areas, because in rural areas we are having 1 to 2 stories building. But if you are providing bamboo band or you are providing wooden band, so you need to treat it with the termite treatment. Termite treatment should be there, or you need to paint it. Otherwise after some time it will turn into the powder. So these are the kind of these kind of horizontal bands. And this, if you can see that one reinforcement is there, and this is called as vertical reinforcement. Like this, you need to provide the vertical reinforcement as well as the horizontal band. If you can see here that horizontal band is there, and this like stapler pin, these are the stirrups. Stapler pin type of stirrups is provided in the bands. So these bands will it will resist your building to split from the corners, as well as it will reduce your unsupported length of the structure. So these are some of the we are having in our rural area some non-engineered kind of a construction is also there. So in non-engineered kind of a construction used to make up of mud. In nowadays also in our rural areas people used to make their houses from mud or mud stabilized block. So there are different kind of now how you can judge that what kind of a mud is useful for your construction or not. So these are the earthquake performance. The earthquake performance of the rural construction is very poor in case of earthquake, rain, flood, because these construction are not engineered construction. The local mason or local people used to make that construction. They hardly consult any architect or any engineer for making their houses. So these construction are having very low strength as well as brittle behavior. Here, in case of earthquake resistance construction, the particular structure must have ductile kind of a behavior, and because in case of brittle kind of a structure, brittle means it will fail suddenly, but in case of ductile kind of a thing, it will give you sufficient warning before collapse. So different type of failure is there: the cracking of the walls, separation of corners, and separation of roofs, and which leads to the collapse to the building. These are some of the the damages which used to occur in the mud kind of a construction. Sometime your roof get your roof get damaged. Your corners will be splitted out. This is called as out of plane failure. See, this wall is overturned because of out of plane failure, because earthquake forces came in a perpendicular direction, and this wall is overturned. So this is called as out of plane failure. Always earthquake cracks can be diagonal cracks, can be along to your beams, can be along to your columns. So earthquake cracks can be there in any direction. So these are a typical kind of a failure in case of mud and non-engineered construction. These are some of the pictures. So how you can judge that the mud is good for your construction. So clay first, the quality of construction, the most important part of clay The clay is the most important component of the soil. It provides dry strength and cause dry shrinkage to the of the soil. So clayey part should be in a sufficient. It should not be more. It should not be less. So clayey part should be in an appropriate quantity into your soil for making your house. And adhesive for strengthening your mud house, you can add the straw, or you can have the non-erodible mud plaster on your wall. And there are different kind of another adhesive are there which you can which you can add into the mud and make your house earthquake resistant. So how what are the codal procedures to judge your whether your soil is good for construction or not? As in your childhood, you used to make the bowls of the mud. In that case, in that way only, you need to make the bowls of the mud. And after drying for drying it in the shed, then you need to crush that bowl into your finger and thumb. And if it will crush, then it is having less amount of clay part. It is a brittle kind of a failure, and it should not be crushed between by your thumb and your fingers. It should not be crushed. So this is the very easy test you can do on the mud, so that you can judge whether it is good for construction or not. Another thing, you by using your both hand, take the little mud and just roll it between your hands. If that length of that roll, if length of that snake type of formation will be there, if that will be in between 5 to 15 centimeter, then the soil is adequate for the construction. If it will break before 5 centimeter, then it is not having the adequate clay part in it. You need to add the clay part. And if it will break, it will not break after the 15 centimeter also. That means the mud is having higher amount of clay part. You need to reduce the clay part. You need to add the sand in it. Another test is that you make the bricks out of the mud, and after drying it, after 48 hours of drying, if you'll see the micro cracks, if you'll see the cracking inside the on the brick, that means your mud is not good for the construction. When another test is there that you need to make one tile, you need to have one brick of the mud. After that, on that brick, you need to stand. If a person is having weight of 60 to 70 kg, he need to stand on that brick. If the brick didn't having any cracks, or if you can stand on that brick, then it is having adequate strength for your construction. Now for making the earthquake resistant principle, it is recommended that if you are making the adobe house, that you are making the house made up of mud, the only one-story building is recommended. Use lightweight roof. If you are constructing your house out of mud, the roof should be very light. Do not use heavy material to make your roofs. Arrange the wall layout to provide the mutual support by means of cross walls. Cross walls should be provided, as you can see in the picture, that cross walls are provided, and the rooms, in case of mud houses, rooms are very small as compared to other construction. And intersection walls at regular interval of time in both the direction. In both the direction, intersection of the walls should be there, and we need to provide. If we are not having intersection of the walls, we need to provide the buttresses to support that wall. Keep the opening in the walls as small as possible, because whenever you are having big openings into your walls, so it will, if the earthquake force will come, it will when inertia force will act on the wall, in case of any action, in plane or out of plane action, very less surface area of the wall is available to resist that force, so that wall will fall. So you need to have very less openings in the walls. In case of recommendation for the earthquake resistant wall construction, walls are the main load bearing walls, and it should not be, the length of the wall should not be greater than 3.5 meter. It should not be greater than that. And the unsupported length of the wall between the cross wall should not be exceed 10 times the wall thickness. It should not be exceed the 10 times the wall's thickness with a maximum of 7 meter. इससे ज़्यादा beyond that it should not be there. The wall opening should not exceed 1/3 of the total wall length. 1/3. It should not exceed the 1/3 of total wall length. No opening should be wider than 1.2 meters. No, 1.2 meters. The opening is the maximum openings. Provide piers of at least 1.2 meters wide between the openings. If you are having opening larger than 1.2 meters, then you need to provide one pier between the opening. So this is this is how you can provide the vertical reinforcement in the construction. It is very easy to provide the vertical reinforcement. Only why we are not providing the vertical reinforcement into our construction? Because of lack of knowledge. We are not having, our masons are not having knowledge that how they can provide the vertical as well as horizontal reinforcement, horizontal bands in our building. In recently also, one of my friend has made his own house. He is very renowned doctor. He's a cancer specialist, and he made his house, but he has spent lakhs of rupees on his house, but nobody knows how to make the earthquake construction. And even his designer, even his architect didn't know the earthquake provision. Now his house is about to be just completed, but still that house is not having any earthquake provision incorporated in that house. So this is only lack of awareness why we are not making our house earthquake resistant. This is a very, very small things which we need to incorporate in our house, and our house will be earthquake resistant. So these, if in some rural areas, some wire mesh, this chicken wire mesh can be provided in place of if you are not having reinforcement, if you are not having bars, so chicken wire mesh can also be provided as a horizontal bands. These are some of the pictures of test. I'll show the real this shake table testing of a structure. So this is how I have explained you in plane and out of plane action of forces. Now this wall, this particular wall is acting as in plane wall, and at the same time adjoining wall will act as a out of plane wall, and it is very weak in direction. It is very weak in this direction because, you know, inertia forces, if you will calculate that BD cube by 12, then D is very less here. But in this case, D is very high. So the resistance to the force is very high. It is strong in this direction, but this wall is very weak in this direction. So this is called as in plane and out of plane action of the force. Now, if you are having, if you have joined these walls well, with by providing the through stones at a different interval, truth kind of arrangement is there. Now see here, if this wall is in plane action of force and this wall is weak, but this wall will support, this wall is supported by this wall because of this joining. It will not separate out. It will not separate out, and it will behave as a one unit. It will behave as a one unit. So that's how the earthquake force behave. And when this force is in this direction, then now this wall will behave as a in plane wall, and this wall will behave as a out of plane wall. But this because of this corner, because of this corner joint of these corners, this behave as a single unit, box kind of a unit. Otherwise, what will happen? This will behave in different manner. This will behave in different manner, and this will collapse. This will overturn. Like this, if you are having unsupported length, larger unsupported length, then it will overturn as compared to you are having shorter length. Okay. Now, in case of, if you are having staircase, in your houses, this staircase is joined by this. Whenever earthquake forces will come, that this staircase will have ponding effect in this kind, is here in this portion. as well as in this portion, as well as in this portion. So it will damage your building from here, and this staircase will collapse. Now if you are having separation gap in between, then this staircase will behave in a different manner, and this your building will behave in a different manner, that both the structure will be saved. Now here you can see the horizontal bands, gable bands as well as horizontal bands in masonry construction. Plinth band in masonry construction, this is the plinth band, this is the lintel band, and this is the roof band in case of masonry construction. And here you can see the gable band, here the roof band, these are the gable bands. Okay, these are some of the collapse which you can experience during the earthquake. Now here you can see the importance of a vertical reinforcement. Now if vertical reinforcement will not be there, you can see this this picture, that if vertical reinforcement will not be there and large opening is there in between the wall, then this portion will behave as a pier. This will behave as a small column that is also not supported by the wall, that is also not connected by the roof as well as your foundation. If that particular column, small brick column, it will behave as a small brick pier which is not connected by the foundation as well as not connected by the roof, and it will try to overturn. If it will try to overturn, the load is beared by the wall. If wall is gone, then your building will collapse. So this is the importance of vertical reinforcement, but vertical reinforcement is recommended in case of zone 5 only. This is how, if the vertical reinforcement is provided, embedded vertical reinforcement bars force the cylinder masonry piers to undergo the bending instead of rocking. It will bend instead of it will rock, it will bend. And one thing you should remember, earthquake forces like wind forces, if wind will travel in a particular direction, it will travel in a particular direction for a longer time. And if it will travel in a reverse direction, after a particular long time, it will travel in a reverse direction. But in case of earthquake, in a particular second, the earthquake force will be in one direction, and at a particular and another second, it will be in the opposite direction also. So it is a cyclic kind of a loading. Cyclic kind of a loading means you are loading one structure and you are removing the loading. You are loading the structure, you are removing the loading, like push and pull kind of a behavior. You are pushing your building, you are pulling your building. You are pushing, pulling, pushing, pulling. Like this, if we need to test our building in case of earthquake for the earthquake loading. So in our laboratory, we used to test our building in push and pull kind of a behavior. We used to construct one wall, and with the help of actuator, we used to test our wall in push and pull kind of a behavior, so that we can simulate our wall by using softwares. We can simulate our we can have the parameters of that wall in the earthquake loading, for the earthquake loading, because it is a push and pull kind of a loading. So here, if you are having openings in the opening also, if you are having horizontal and vertical bands, so this opening, when the wall with an opening deforms during the earthquake shaking, the shape of the opening distorts and become more like a rhombus. एक rhombus की तरह बन जाता है. It will look like a rhombus. But if you have provided the vertical and horizontal reinforcement, again your pier will bend, rather shaking. If suppose two piers are there, you are not having any vertical reinforcement. Now these two piers will rock. Now this pier will rock in X direction, and this pier will rock in Y direction. So if you are having vertical reinforcement, that both the piers will rock in a one direction. So your opening will be saved. This is how the mud wall collapse if you are not having through stones in between the walls, because when the earthquake force will be there, then the splitting of the wall will be there. The two portion of the wall will be split from the middle portion, and it will collapse. So these are some of the pictures of the pattern of how these corners. Here you can see that out of plane failure, and the corner is failed because of that. This is also separation of unconnected adjacent wall. This room and this room, you cannot see. Here are two rooms, and one wall of one room is not connected with the other one. So that's why it failed. Now here in this picture you can see that the person have provided the band, but that band is not continuous. Here the band is here discontinuity of band is there. The person is right, he has provided the band, but the discontinuity of the band is there at this portion. So the band should be continuous so that it can have a box action during the earthquake. Otherwise it will not work. If the discontinuity of the band will be there, so it will not work. Though unsupported length of the building will reduce, but still the performance which need to be done by the building during earthquake, it will not be there. So this is how this another picture is how you can have the different through stones at the different interval, at least 600 mm away from each other. So this is how you can have the through stones. So at the concluding remarks, if you are having your building having light roof structure connected together, horizontal and vertical reinforcement, regular and symmetrical buttresses should be provided, flat and firm and dry site, and good quality of construction, then your house will be happy. So now after this lecture, we'll see small 10 to 15 minutes video film in which you will see that the structure, different kind of a structure, one structure made up of brick, another structure made up of mud blocks, another structure made up of rubble masonry, another structure made up of stone masonry. So how those structures behaves during that earthquake, and how you can provide the vertical and the horizontal reinforcement in that structure. And the structure is tested in the earthquake engineering labs, and you can see that film.
This could be you or me, as in the last 5 major earthquakes, over 2 lakh Indians died without even knowing what wrong with them. Thankfully, we survived. And we should stop and think what we can do to protect ourselves and generations to come from the wrath of earthquakes. India, like several other countries of the world, is prone to earthquakes. On the basis of earthquake risk, India is divided into 4 major seismic zones. The red zone is the most vulnerable to major quake activity, and the green area comes a close second. We construct houses and other buildings to live, work, and to protect ourselves against the natural calamities. But do we truly bother to ensure a long-lasting and safe building? Many of those who died could have been with us if they knew how structural engineers and architects use some of the fundamental principles of physics and mathematics to create buildings which can absorb, disperse, and withstand strong seismic forces. Those of us who had incorporated these features in their building structure survived with least to nil damage. As the structural scientists say, earthquakes don't kill, unsafe buildings do. In India, over 85% of the population lives in masonry buildings. The Disaster Management Division of Ministry of Home Affairs, Government of India, referred a project related to the testing of masonry buildings to the Department of Earthquake Engineering, Indian Institute of Technology, Roorkee. The idea is to formulate and effectively demonstrate the efficacy of seismic strengthening of the popular three types of masonry buildings: brick, block, and stone masonry. The experiments are to be conducted on the railway wagon shock table testing facility available at the department.
Shock table provides a 36-meter long railway track having mild gradient on either side. The rails are marked at half-meter intervals as a guide for positioning the wagons before releasing to achieve the desired impact. Shock table forms a rigid steel platform which is used as a base for dynamic testing of building masonry models. 10 helical steel springs have been mounted on both ends of the table to convert the impact into a quake-like wave. Loaded wagons are placed on the track inclines on both sides of the shock table. The weight of each wagon is adjustable. The wagon on the left side is allowed to roll down the incline to collide with the shock table platform. Due to the impact, the shock table wagon starts to move and collide with the other stationary wagon on the right side and receives impact in the reverse direction. In this way, the model construction on the shock table receives two shocks simulating an earthquake-like motion. The intensity of the shock is controlled by positioning the loaded wagon at different distances on the track incline before release for rolling down.
Two half-scale, single-room brick masonry models are constructed simultaneously on the shock table. The first model is constructed using popular construction techniques as we have been doing for years. This model has been constructed without any earthquake-resistant features. In the second model, all seismic strengthening arrangements specified in earthquake safety codes like vertical reinforcing bars at the corners, jam steel around the openings, and seismic band at lintel level are incorporated. As per chosen scale, half-size bricks are laid in 1:6 cement sand mortar, providing space for the vertical steel bars at the corners and near the openings. The gap along the vertical bars is filled in 1:2:4 concrete mix with 6 mm size aggregates after every 5 courses of the wall construction so as to develop full bonding. The walls are completed up to the lintel level and a monolithic horizontal seismic band is provided on all 4 walls so as to integrate the perpendicular walls. In the actual construction, vertical reinforcement is embedded in the plinth masonry into the foundation and is passed through the lintel band and anchored into the roof slab to develop its tensile strength. The reinforced concrete band has the same width as the thickness of wall. The vertical thickness is kept to the half scale. Then the wall is completed up to the roof level and the roof slab is laid as was done for the traditional model. The two models look exactly the same. The traditional model is constructed using conventional techniques, while the earthquake-resistant model incorporates corner vertical steel bars, jam steel bars around the openings, and horizontal seismic band on all the four walls at the lintel level, which will be safe if an earthquake occurs. We shall see by impacting the shock table. Before testing, the table and models are instrumented using acceleration meter to measure the intensity of the simulated earthquake and the effect on the models. In the first shock, the loading wagon hits the shock table from the left side, simulating a low intensity shaking. With each subsequent shock, there is a gradual increase in the intensity of the shocks. So, what do we see? Even after the fourth shock simulating an earthquake of severe intensity, no damage is seen in the masonry model with earthquake-resistant features. But the conventional model is badly damaged. The fifth shock is made even stronger. The model with earthquake-resisting elements still remains undamaged.
This is the wall in the same line as the direction of the shock. So this has the behavior of out-of-plane bending. Now as we go, we see here how this wall tends to fall out. And then when we come to this wall, this shows different behavior than this particular wall, because this is now in the position of a shear wall. And a shear wall has a behavior of the shear failure, as we can see here. It's a diagonal tension failure. So we see here that this unreinforced model constructed in the traditional manner is failing. On the other hand, this is a model of the same type with the same geometrical details, same dimensions, same wall thickness, same roof thickness. So everything, mortar, etc., everything is the same. But the difference is it has vertical reinforcing bars at the corners, all the four corners. It has also vertical bars at the jambs of openings, as we can see here, window jambs and the door jambs. And also it has a seismic belt or band actually, which is going inside all around the building. Now these reinforcing details are keeping the whole building intact and in very much integrated behavior of all the walls put together. So you can see the difference.
Earthquake strengthening of buildings could have saved thousands of lives in Bhuj, Latur, and Kashmir earthquakes. At places where it is difficult to get bricks, people use concrete blocks for constructing buildings. Therefore, the second set of tests is conducted using concrete block masonry construction. Solid concrete blocks of half size have been used to construct two half-scale similar models on the shock table. Both the models are constructed in the same way as the brick models were constructed. For construction of the wall with corner steel and jam steel near the door and window openings in the earthquake-resistant model, special blocks with semicircular holes are used. The two models differ from each other as the strengthened model additionally has corner vertical steel bars, jammed vertical steel bars around the opening, and horizontal seismic band on all the four walls at the lintel level. During the testing of the models, shock table is imparted shocks of gradually increasing intensity. In the shock equivalent to a moderate intensity quake, cracks started to form diagonally at the corners of the window openings in the traditional model and gradually spreading towards the corner of the wall. Horizontal cracks are also visible just above the lintel beam, extending to the end of the wall and reaching up to the corners. There is a slipping of the wall from the foundation. These are typical shear cracks observed in masonry buildings after a moderate-sized earthquake has struck the region. However, the earthquake-resistant model remains undamaged even after this shock. For the next shock, the loading wagon is placed further up on the incline to simulate an earthquake of severe intensity, which could occur in higher earthquake zones 4 or 5 in the green or red areas as per the seismic zoning map of India. The traditional model further loses its strength and stiffness. The next shock is of slightly higher intensity as compared to the previous shock. Here too, the earthquake-resistant concrete block masonry model shows no sign of distress. There is no damage and the model is intact even after imparting a severe intensity shock to it. In the next and final shock, the intensity of shock loading is further increased so as to check on the strength of the earthquake-resistant model under a much more intense shock. The performance of the earthquake-resistant concrete block masonry model is indeed being put to the ultimate test under this shock loading. Traditional model could not withstand the severe intensity shock. However, there are no cracks in the earthquake-resistant model. The earthquake-resistant features have improved the building under earthquake shaking. India is a collage with myriad cultural and religious colors. The diversity in India is even spread across its geographical terrain. As a result, at different places, people construct buildings using different materials available locally. Like in the hilly areas, one would see that a majority of buildings are made using stone masonry construction. The loss of lives in earthquakes of Uttarkashi, Chamoli and Bhuj underscored the necessity of earthquake strengthening of the stone masonry buildings. Two half-scale single-room models are constructed on the shock table. As before, the first model is constructed using traditional construction techniques used by common man. While constructing the earthquake-resistant model, features like the corner steel and the jam steel around the openings are placed so as to develop tensile strength. For providing vertical bars in the stone masonry, casing pipes with a diameter of 50 millimeters are placed around the steel bars, and the masonry is then built. After construction of 3 courses of masonry, the casing pipes are raised and the cavities are filled with concrete mix and compacted. In the construction of walls, through stone or header is placed at regular intervals. In each layer at the corner, a long stone is put into the alternate layers of walls, strengthening the building structure. A horizontal seismic band is provided on all 4 walls at the lintel level. In the stone buildings, another horizontal seismic band of the same dimension as of the lintel band is provided on all four walls at the eaves level, and gable band is extended up from this band. In the earthquake-resistant masonry model, wooden trusses and cross bracings are used instead of the usual rafter system in the roof. In order to prevent sliding of the roof tiles, they are bound with wire mesh at the ridge and the edges, and concreting is done on this mesh. The two masonry models differ, as the strengthened model has wooden trusses and cross bracings, header or true stones, cornerstones, corner vertical steel bars, jammed vertical steel bars around the openings, horizontal seismic band on all the four walls at the lintel level, horizontal roof band on all the four walls at the eaves level, and gable band at the two ends reaching up to the tiles or gable walls. The models are subjected to shock loading, each with increasing intensity. This shock is similar to an earthquake of a severe intensity, likely to occur in Zone 4 areas in the seismic zoning map of India. This resulted in cracks opening up in the traditional model, whereas the model with earthquake-resistant features showed no distress, a visible proof of the strengthening of the building structure. For the final shock, we take the loading wagons further up on the incline and release. The resulting shock simulates a very severe earthquake likely to occur in Zone 5 on the Indian seismic zoning map and affecting cities like Bhuj and Chamoli.
First, the corner has opened out, and then the diagonal cracks had appeared. And this is the beginning of the collapse of the building. If we provide the seismic belt like this throughout the building, and which holds all the walls together, then the cracks will not develop, and then it will not initiate the triggering of the collapse of the building, and it will be safe.
Yes, indeed. But how much extra does it cost to build an earthquake-resistant house? Well, it will cost just an additional 5 to 6% of the cost of a traditional building and ensure complete safety for the family. A safe dwelling unit is equally necessary and important for those of us who have already constructed a house and cannot afford to rebuild due to financial and other limitations. Hence, there is a need for external strengthening of the already existing buildings. This is known as retrofitting of the existing structures. Traditional model is prepared for incorporating earthquake-resistant features post-construction. For putting the header or true stone, few stones at regular intervals are taken out from the walls. These holes are then filled with an S-shaped iron rod, an M15 grade concrete mix. For corner steel, wire mesh is nailed and plastered. Similarly, other earthquake-resistant features like jam steel, lintel band, roof band, and gable band are incorporated externally. For preventing sliding of roof tiles, they are secured by wire mesh and concrete, as was done while constructing earthquake-resistant model. Now, on the shop table, we have two similar models. These two have the necessary strengthening features, retrofitted in one while built in the other. For the first shop, the loading wagon is released to generate a low-intensity earthquake. With each subsequent shock, there is a gradual increase in the intensity of the shock within. It is clearly visible that both the models are showing the desired results. Even after a severe intensity of simulated earthquake loading, there is absolutely no damage in either of the models. Constructing a new building with seismic resistance increases the cost by 5 to 6%, while retrofitting an old house will cost 10 to 12% of the reconstruction expense. But incorporating earthquake strengthening features makes a huge difference, the difference between life and death. These tests prove beyond doubt that earthquakes don't kill, and the structures with safe design and construction will neither collapse under the impact of an earthquake nor kill the inhabitants. Buildings constructed with proper care and incorporating earthquake-resistant features have successfully withstood the wrath of earthquake even at places like Bhuj. You can safeguard generations to come by building structures which have earthquake-resistant features like the vertical jam steel around the door as well as the window openings, vertical steel at all the corners, horizontal seismic band on all the four walls at the lintel level in the stone masonry structure, additional roof and gable bands. These features, at a very little additional cost, would make the difference between life and death, not only for you, but also for your loved ones. Remember always, earthquakes don't kill.
So this is all about the earthquake measures in case of masonry, in case of stone masonry, in case of blocks, in case of brick masonry. You have seen the provision incorporated in the earthquake resistant construction, as well as the retrofitting models, how they have performed during the shock table test. This shock table test has been made in the Department of Earthquake Engineering for simulating earthquake kind of conditions, and we used to compare it with the different kind of performance of the building with different kind of earthquakes which happened in the past, like Nepal earthquake and other earthquakes. We have various damage parameters which we use to compare by using this this shock table test. In another features, we are having shake table testing in the laboratory. So now I have shown you all the parameters and what are the provisions which need to be incorporated in case of masonry and in case of RCC construction. We have seen few video films. Now if you are having any query, so we'll take up queries for 5 minutes. So after that we'll close the session and we'll meet tomorrow.